Hi, and welcome to Interspeech 2020. This video presents a deep 2D convolutional neural network for waveform-based speech recognition, joint work by Dean Oglitch, Zoran Cvetkovic, Peter Bell, and Steve Reynolds. Scalable and effective acoustic models are typically based on handcrafted features, designed according to the physiology of human hearing and psychoacoustic measurements. The most effective and widely used feature extraction techniques, such as FBank and MFCC features, are based on bandpass filtering of speech signals. Potential shortcomings of these feature extraction techniques find that parameters specifying such representation are fixed a priori and not learned using the available data. Additionally, information loss inherent to waveform compression performed by these operators can adversely affect robustness. As the feature extraction is done independently of modern learning, it doesn't provide ideal inductive bias. Moreover, phonetic events, the boundaries of short frames characteristic to spectrograms, are typically poorly described by filter bank features. To tackle these shortcomings, we propose a neural architecture operating directly in the waveform domain. Previous work has already identified several challenges when dealing with raw waveforms. For instance, speech waveforms are characterized by a large number of variations in form of phase shifts and temporal distortions. The input space is also high-dimensional, and this can prolong the training time. And an effective neural architecture operating directly in the waveform domain needs to be capable of automatically extracting features that are invariant to small phase shifts, stable under small perturbations that distort or warp signals, invariant to nuisance transformations such as translation in spectrotemporal decompositions. And it also needs to be able to embed redundancies into the representation such that it could withstand a fair amount of additive noise and degradation without significant overlaps between different phonetic units. The proposed neural architecture can be characterized by four components. The first one performs sub-band decomposition of the input signal using parse and filters. The second component uses standard wide-pass convolution filters with max pooling to compress the structured high-dimensional sub-band decomposition into a low-resolution spectrotemporal representation. The third component employs classic 3x3 two-dimensional convolutional filters and extracts relevant features from previously generated low-resolution representation. The final fourth component is a multi-layer perceptron. The sub-band decomposition block is realized via parametric convolutions. What this means is that we have a functional form that generates filter values for standard 1D convolutional operators. We opt for parse and filters that are defined using cosine modulations of compactly supported Parson windows. This particular window function is known as the squared Apanachnikov. By changing the modulation parameter eta and window width parameter gamma, we can generate filters with different bandpass properties. In this particular illustration, the filter support is 401 sample, which amounts to approximately 25 milliseconds of raw speech sampled at 16 kHz sampling rate. In some cases, the filter occupies the full support, as in the image on the left, and in others, it's concentrated around the central sample, as in the image to the right. As illustrated in power spectrum representation, change in eta that controls the modulation frequency can move the bandpass region across the frequency axis. The window width parameter, on the other hand, controls the bandpass width, and that bandpass width is inversely proportional to the window width. Thus, we can control the bandpass properties of the filters with only two parameters, eta and gamma. Having generated filters with support size of 401 sample, we use the standard 1D convolutional operator to extract the subband from the input signal. In particular, the generated filter vector is used as a 1D convolutional filter and just convolved with the input signal using a stride of one sample. By taking this filter and convolving it with the signal and moving to the right, we obtain a subband for that particular filter. If we repeat this process for the specified number of filters, we will have obtained a subband decomposition. In our particular case, in all of our experiments, we have used 64 filters. Thus, as a result, we obtained 64 subband signals from the input signal. The subband decomposition is further max pooled for translation invariance purposes. As you can notice now, the decomposition has increased the dimension of the input space and embedded the signal into a high-dimensional space of spectrotemporal patterns. Now go to the second component of our approach, where the aim is to extract a low-resolution spectrotemporal representation from the high-dimensional subband decomposition. The first step of this stage, we embed the subband decomposition into an even higher dimensional space by means of a 2D convolutional operator. The aim of this step is to allow a network to embed redundancies into its representation, such that it could withstand a fair amount of additive noise and channel degradation, while still keeping separability between the representation of different phonetic units. For this purpose, we use a 2-dimensional filter with 11 taps over frequency subbands and 5 taps over time. Following this, we start to compress the representation in order to extract a low-resolution spectrotemporal representation. This is achieved by using double convolutions with 5x5 filter size. We use double convolutions to allow for a potentially larger or wider reach of the convolutional filters and introduce more flexibility into the convolutional operator in this way. The compression is achieved using the max pooling. The combination of convolutional and max pooling operator is known to yield translation invariance, which is something we want to achieve in the spectrotemporal representation. At the end of this stage, the network extracts the low-resolution spectrotemporal decomposition of dimension 32 times 35 with 32 channels. Previous work has already demonstrated the effectiveness of standard 3x3 convolutional filters on such low-resolution representations. Motivated by this, we used 2 blocks of double convolutions with filter size 3x3, coupled with max pooling, to extract a set of features representative of an input speech frame. The outputs of this block are passed to a multi-layer perceptron with 4 hidden layers. In each hidden layer, we use 1024 units. Throughout the network, we use the value activation function. With multi-layer perceptron, we use batch normalization, while in convolutional layers, we use layer normalization. The approach has been evaluated in different acoustic conditions by training hybrid HMM-DNN models on TIMIT, Aurora 4, and AMI. In all of these experiments, the approach consistently outperformed previously proposed models for row speech. This bar chart illustrates the performance of the approach on the TIMIT dataset. We have compared to 4 baselines for row speech: SyncNet, SyncSquareNet, row speech CNN, that's a CNN operating directly on row waveforms, and end-to-end CNN, with an initial layer that is initialized using parametric filters. Our Parsons 2D network clearly outperforms all previous approaches for row speech. Moreover, we also compare to state-of-the-art feed-forward approaches employing handcrafted features, and show this way that learning directly in the waveform can be more effective. More specifically, we show that the approach outperforms a junction architecture designed for deep scattering spectrum, as well as challenging FMLR features combined with an MLP and MFCC with MLPs. The second experiment, our aim is to demonstrate that the architecture is capable of learning a noise-robust representation. For this purpose, we simulate an experiment on Aurora 4. The bar chart provides a summary of our results using DNN and GMM alignments. For row speech, we use the SyncNet as the baseline. That's the most recently proposed method that is considered to be state-of-the-art. Irrespective of the used baseline, we showed that the Parsnip-2 architecture is significantly more effective than the SyncNet architecture. We then compared two architectures designed for handcrafted features. In particular, we compared to VDCNN that employs 10 convolutional layers on top of FBank features, and multi-octave convolutional network proposed recently that employs 15 convolutional layers. The empirical results demonstrate that the Part2D with GMM alignments outperform both of these approaches. The experiment thus indicates that learning directly in the waveform domain can be more effective than learning with handcrafted features, and that architectures designed to operate directly in the waveform domain are capable of learning robust representations. The final experiment is on conversational speech using the AMI dataset. Here we demonstrate that the approach significantly outperforms two recently proposed approaches for raw speech. Particularly, we compare to the SyncNet architecture and a multi-span convolutional neural networks. Our Parsnip-2D architecture is significantly more effective than both of these architectures. We also compare our approach to architectures designed for handcrafted features. In particular, it is known that time-delayed deep neural networks are state-of-the-art for this dataset based on handcrafted features. We show that our Parsnip-2D architecture performs on par with TDNN, trained on top of the FBank features without I-vectors. The experiment thus shows that the architecture generalizes even to the conversational speech. In summary, we have proposed a novel architecture for waveform-based speech recognition that consistently outperforms alternative approaches on both noisy and conversational speech. We have provided a comprehensive empirical study showing that learning directly in the waveform domain can be more effective than learning with handcrafted features. We have reported state-of-the-art results for waveform-based speech recognition on noisy and conversational speech. The approach is capable of learning in noise-robust representation or Aurora 4, and it does not overfit on a small thin dataset. The code is released through my homepage. Thank you.